Hello guys, welcome back to Foolish Engineer. SOC is not a physical measurement but a calculated guess. There are two basic and simple techniques to calculate state of charge of a battery. One is open circuit voltage and another is Coulomb counting. The voltage method is cheap and never trades, but it is a liar and goes blind for most of the batteries. Coulomb counting is basically counting current going in and out, but it has some problems too. Let's say more about that in detail. In our old petrol cars, measuring fuel was a piece of cake. We had a plastic tank, we had a floaty ball on a stick, which gives the indication. If the ball was at the top, we were good to go. If the ball was at the bottom, our tank is empty. But a battery is what we engineers call a black box. We can look at this cell right here. Can we see the electrons? No. Can we weigh them? Absolutely not. Can we hear them? Well, only if the electrolyte starts boiling, and by then it is way too late for us to be asking any questions. Technically, we define SOC as the ratio of the current capacity, we call it Q of T, to the rated capacity of the battery, which we call Q of N. We use a specific formula for state of charge at any given time. But because the box is black and opaque, our BMS has to act like a detective but with a lot of multimeters. The first clue we use is the basic one, and unfortunately that lies to us the most, which is voltage. We need to think of voltage not as electricity but as electrical pressure. Imagine a balloon. When it is full of air, the pressure inside is high. It is tight and ready to pop. If we just let little bit of air out, that long high-pitched squeaking sound we hear, that is the pressure dropping. Batteries are exactly the same. A fully charged cell has high pressure, which we measure at high voltage, and an empty cell has low pressure. To track this, we use a tool called open circuit voltage to SOC lookup table. This is the voltage we measure when the battery is just sitting there on the shelf. Here's how the OCV table looks like for a standard lithium-ion NMC cell. At 100% SOC, we see a pressure of 4.2 volts per cell. At 90% SOC, we see pressure of 4.01 volts. At 50%, we see pressure of 3.7 volts. At 10%, we see around 3.3 volts. And at 0%, we see around 3 volts per cell. It seems very simple, right? When we measure 3.7 volts, we look at our cheat sheet and boom, 50%. Case closed, case finished. Well, it's not that easy. This is where the foolish part of our engineering comes in. If we just finish charging our battery and we measure the voltage, it looks really high. This is what we call surface charge. Let's imagine a bottle of Coke. If we shake it up vigorously, the pressure inside looks massive. But do we have more soda in the bottle? No, it's just agitated. Inside our battery, during charging, lithium ions are like a massive crowd of people trying to get into a stadium at a time. They all pile up at the gates. That is basically the surface of the battery plates. They haven't had time to soak into the deep chemical layer. If we take a reading right now, a BMS thinks the battery is fully 100% charged. But it is actually just a fake voltage spike. To get a real honest reading, we need the battery to rest. After charging, we need at least 2 hours for the ions to settle down. After discharging, we need at least 5 hours for the chemistry to stop panicking. Who has that much time to wait the dashboard to tell what's the truth? Nobody. Plus, if we measure voltage while the battery is working, we get the voltage sag. The internal resistance makes it look like we are empty when we are actually just working hard. That means if the battery is loaded, it will shoot very much current, but the voltage will drop. Although the capacity of the battery is not reduced that fast, but still the drop is there. One of the key reasons I started this YouTube channel is to bridge the gap between the outdated Indian education system and actual skills needed in the industry. Well, if you're a student, you can use and learn an industry leading EDS software, Altium, for free by using its student lab program, which narrows down this gap. You just need to use your university email to enroll, and you get a full student license, a full PCB design course, and a certificate recognized by top Indian core electronics industries. Altium isn't just one PCB design software, but it is a whole platform of capabilities for electronics design. I've personally used Altium since the start of my electronics journey, and I honestly recommend it. It's a fantastic way to enhance your skills and increase your chance of landing a job in a core electronics company. So don't miss this golden opportunity. Since we can't trust the pressure while our battery is actually working, we have to count what goes in and what comes out. We call this Coulomb counting or current integration. Imagine a bathtub. If you know exactly how many liters per minute water is coming out of the faucet, and we have a stopwatch to measure the time, then we can calculate exactly how much water is in our tub. That's how the Coulomb counting works. We use this math and this is what it looks like. For this, SOC at a time equals to an initial state of charge plus 1 by the rated capacity times the integral from a starting point to a current type of the efficiency coefficient times the instantaneous current. Well, in plain English, it just tells us our current charge is equal to where we started plus the total amount of electricity that flowed through our sensor. It's like we have an accountant keeping an account of every single electron that crosses the terminal border. No more guessing, right? Wrong again. Math has a dark secret, which is cumulative error. Let's see what is that. Every sensor we put in a BMS has a noise floor. For example, most of our BMS shunts, anything below 0.5 to 0.8 ampere is basically invisible. It is like a small leak in the bathtub that our accountant can't see because it is too small to notice. Imagine we have a single 100 ampere hour battery with a 0.5 ampere ghost load, maybe a small cabin light. A BMS sensor reads this as 0 amperes because the shunt can't detect this low current. On day 1, we actually lost 12 ampere hours. Our BMS says 100%, we are full. On day 3, we lost 36 ampere hours. Our BMS says still 100%, we are geniuses. On day 7, we lost 84 ampere hours. The battery is basically dead. But our BMS, it still says 100%. Yay! Then suddenly, poof! The voltage hits the cliff edge. Our BMS triggers a low voltage disconnect to save the cells from permanent discharge. And our lights go out. We're left in the car screaming at an app that still says 100%. We call this SOC drift, and it is the reason we hate such EV BMSs. With a normal NMC battery which we have in our phones, the voltage is a nice cooperative sloping slide. Every 1% of charge drop comes out with a clear measurable voltage drop. It is easy for us to track. If you still think those standard batteries are tricky, we need to look at the lithium iron phosphate or LFP batteries. These batteries are the worst for SOC estimation. They are the reason we battery engineers have grey hair and twitchy eye by the age of 30. I'm one of them. From 90% all the way down to 20%, the voltage is almost a perfect flat line. It stays parked around 3.2 volts to 3.3 volts for almost entire cycle. Is this an 80% charge or it is 90%? We don't know, our volts don't know. a tiny millivolt measurement error of an LFP cell can result in 50% SOC error for us. This is why LFP batteries absolutely demand Coulomb counting. But since Coulomb counting drifts like a boat without an anchor, our LFP systems are famous for SOC jumps. If our voltage method is a liar and our flow method is a drifting mess, how do we get back to reality? That's where we need a sync point. We call this the 100% reset. To hit the reset button on our math, our BMS waits for the ceiling. For this, three things must happen at the same time. First, our voltage hits the charge voltage limit. For example, a 12 volt LFP system that is usually around 14.4 volts. Second, our current drops below the tail current during charging. This is usually 2 to 4% of our battery's capacity. It means our battery is so full, it literally cannot accept any more electrons. And third, dwell time. We need these conditions to stay stable for 3 to 5 minutes to make sure it wasn't just temporary fluke or passing cloud. At that magic moment, our BMS says, aha, I don't care what my drifting math says, we have hit the ceiling. Reset SOC to 100%. This clears out all the math tolerance that accumulated from our invisible leaks. This is why we must charge our batteries to 100% at least once every few months. If you only cycle it between 30 to 70%, our gauge will eventually become a work of pure fiction. Now we need to get more serious for a moment. We have to talk about why they fail us in the real world. First is the temperature. When it gets cold, electrolyte inside our battery becomes thick and viscous. It's like we are trying to run through a pool of thick gel. At low temperatures, the battery's resistance spikes. This causes a massive voltage sag the moment we draw any current. Our high voltage packs are made up of hundreds of cells in series. But here is the catch. The SOC of our entire pack is dictated by the weakest cell. Yeah, exactly, the weakest cell. If we have 95 cells at 80% charge and one lazy cell at 10%, a BMS must shut down the whole system when that one lazy cell hits the bottom. So, our dashboard might say 50% SOC at one time because it is averaging things out, but then it suddenly drops to 0 because that one weak cell tripped a safety alarm. A math is only as good as a weakest cell. Our batteries suffer from old man syndrome. As they age, they lose the capacity. A battery that has 100 ampere hours 3 years ago might only be 80 ampere hours today. But if our BMS still thinks it is 100 ampere hour bucket, all of our math for Coulomb counting is wrong. It thinks that after drawing 50 ampere hours, we are at 50%, but in reality, we are at 37% of our new capacity. Unless our BMS is smart enough to track our state of health. Well, that part we'll call later on. So, in summary, we know both methods are basically useless if our cells are unbalanced, our battery is old, or it is freezing outside. So, what is the solution? We use math. But explaining that requires way more coffee and a much bigger imagination. So, let's save that for part 2. If you found this video useful, give it a thumbs up, hit the subscribe button, and stay tuned for more exciting content.